Are you okay? Are you ready? Yeah. Okay. Okay, so we're happy to have Ju here who will tell us about the Center of Small Quantum Groups.
Great, thank you for the invitation, and it's a great pleasure to come back and visit and give a talk. Thank you. So, the talk is on the Center of Small Quantum Groups. This is a joint work with Anna Hofska from the Polytechnic University in Lausanne in Switzerland. So, as we will see, the Center of Small Quantum Group was surprisingly a very unknown problem until last year. I guess here I'll try to report some progress. So before doing that, let me give you some background. So what is the small quantum group? But to start with, I think we should find a more classical analog in modular representation theory. So if G is a finite dimensional complex semi-simple of finite dimensional Lie algebra. So a lot of people like Constant, Lutzig, Chavalet, and a lot of algebraists, representation theorists spend a lot of time trying to define what it means to study representation theory over the ring of integers. So in particular, one problem is how do you study representation theory of G over a field of finite characteristic. So in particular, so over a field of characteristic P, or a finite field, maybe over a field of characteristic P, there is the so-called the analog of universal enveloping algebra of UG, which is defined by this what people usually call this distribution algebra of G. So this is generated over Z by the divided powers and specialized at root of unity. So specialized at finite characteristic. So if you think about it, these are generated by EI, Fi divided powers subject to the relations, etc., HIs, where I is the Medgar datum of G. Then there is a Frobenius map from the distribution algebra onto itself, which sends UI, EI to the M is mapped to EI M divided by P if divisible, if he divides M, or 0 otherwise. Likewise for F and H. So this is the so-called Frobenius map on the algebra level. So the kernel of this map is the restricted algebra U1 of G, which I write really small because this is analog. This is finite dimensional. This is finite dimensional of algebra. So this sequence is the analog for algebraic groups. If you study algebraic groups over a field of finite characteristic, there is a Frobenius map raising every coordinate to degree pth power, and the kernel is a finite group with coefficients in the finite field. So this is analog in the algebra story. For this story, well, to study quantum groups, Lutzig introduced a notion which is a parallel to this story in characteristic 0. So let's define a characteristic 0 analog for quantum groups. Quantum groups, which can be written roughly as, so you have quantum groups at a root of unity. So here now this fix Q is an L's root of unity in C, a primitive L's root of unity. So UQG is a quantum group. You quantum deform everything. This is quantum Frobenius map going into the. Unfortunately, here this is not going from quantum group to itself, but here it goes to the classical algebra over C, and the kernel is what people usually call the small quantum group, which I should write very small. You notice the difference. This by font. By generators and relations, for instance, for example, if G is SO2, you can write this quantum group very explicitly. So UQG can be written as the C algebra generated by E, F, and K inverse, modulo those relations like E, F equals K minus K inverse, Q minus Q inverse.
Is it over C or over some other way?
Over C, complex numbers. But when you have the integral structure, you can make out of like just pick Z adjoint Q, so that's a cyclotomic field, cyclotomic ring of integers. But for complex, you can just present everything over C. These are the relations. You can write them down explicitly. The usual quantum group relations, and K inverse is Q squared. K inverse is K minus 3. And what makes minus F? And what makes it small is because of some nilpotency relations that make it finite-dimensional. So e to the L power is F to the L power is 0, and K to the L power is 1. So the truncation makes it a finite-dimensional algebra. So if you use the base change from some cyclotomic ring of integers into FP, you recover the restricted algebra. Right. So now in the study of finite-dimensional algebras, so you want to a very central question is what's the center of this finite-dimensional algebra? Right? So question, a natural question you want to ask. So one of the easiest questions: if A is finite-dimensional algebra, not necessarily commutative. So what's the center? The natural commutative algebra associated to A. So we want to ask this question. So the question is very natural. So for both this finite-dimensional algebra, the finite-dimensional Hopf algebra U1G, for small quantum group UQG rooted unity. So, well, these guys, the study of finite-dimensional Hopf algebra U1G, which is the restricted Lie algebra, or the small quantum group, have been defined. Well, that guy is defined in the 1960s by Chavalet and many classical giants in representation theory. And this is defined by Lustig in the 1980s, but so had more than 40 years, over almost 40 years of history. But the question remains wide open what the centers are for this finite-dimensional algebra. So I'll report some partial progress relating to these two cases, but what's nice about these algebras is, well, I'm going to give you quote the following theorem of Anderson, Janssen, and Zirkel. Which says that this is really a God-given or natural object to study in this setting, right? Which says the algebra structure of the centers of the, I should say, the regular block of the principal block. I'll explain this notion afterwards. The principal block of UQ G is actually independent of the order of Q. It's independent of the order of Q. So furthermore, if you base change the cyclotomic ring, if ZQ, if Z, UQ, G, base change over the cyclotomic ring. Let me write this as ZQ to a field of finite characteristic K. This is isomorphic to the center of U1 G for the restricted algebra. So what do I mean by the principal block? Well, here a finite dimensional algebra A can always be decomposed into indecomposable products A1 cross A2 cross AR. So each of AI indecomposable algebra. So the first one, so A1, where for these two algebras, U0, we call A1. For this out, where UQ, G acts non-trivially on the trivial representation, which is a mouthful, sorry, trivially on the trivial representation. There is a unique subalgebra that acts non-trivially on the trivial representation. Well, this corresponding algebra is called the principal block of the algebra. So the beautiful famous theorem of Anderson, Janssen, and Zerbo is that this algebra, center of this regular principal block is actually independent of Q, and furthermore independent of characteristic P you choose here, and it's controlled by the same algebra, same commutative algebra here. So it's, whenever you're given a Cardan datum, we know that by Chavalet's classification, there's only finite many families of them. Given a given dimension, there's finite many of them. So there's a finite many, for a given dimension, there's finite many commutative algebra that controls representation theory, root of unity or prime characteristic. It's quite surprising. But,
and it's the principal block here matching up with the principal block on the classical side?
Yeah, it does. Okay. So, well, to give some interpretation, so how we actually computed is through so-called algebraic geometry or geometric representation.
Sorry, in the singular, in the other blocks, it's not true, or?
It's also true.
Okay.
Janssen's translation is also true. Yeah, the other regular blocks are equivalent to singular blocks.
So this is the main content, and then using translation, you get the other.
Yeah, okay. But there are also singular blocks, which is slightly different.
Okay.
Other questions? All right, so I'm going to give you a geometric interpretation back in the 80s. So due to the mathematical giants, Bernstein, Bellingson and Bernstein in another set of problems, so geometric interpretation. Which is this is the famous localization theorem of Bellingson and Bernstein. Which, well, when they studied instead of the small quantum group or restricted algebra, they studied the classical problem of the universal enveloping algebra of G over complex numbers. So what they did was, well, they studied the corresponding regular block, principal block of this complex semi-simple algebra, a universal enveloping algebra, and used the geometry of black varieties and interpreted the representation theory correspondingly. So roughly speaking, so let G be a G, again, a complex semi-simple the algebra over C, and let G be the corresponding complex algebraic group of adjoint type. So if you want, for the whole talk, you can pretend G to be concrete, to be SLNC, and the corresponding group is G is just the set of n by n in determinant 1 matrices quotient the center, quotient of roots of unity. So e to the psi times the identity matrix, where psi is the root of unity. Nth root of unity. Okay. So these are this is the center of SLM by Schur's lemma. Right. So let's fix a Borel group. So B is a Borel group, Borel subgroup, which in this case we can take to be the set of all upper triangular matrices. Right, inside this group. So then X equals G mod B is the so-called flag variety. For the algebraic algebra or algebraic group. So what did Beilinson and Bernstein do? They said that, well, we can translate the study of algebraic problems in for UG into the geometry and relate this to seemingly completely different subjects. Right. So the representation theory of this guy is related to the geometry of this guy. But how is this given? So roughly you can consider. I'll also denote n tilde the associated piece, the cotangent bundle of X, which is the Springer variety, or Springer resolution of the Neopointed co. So this is the cotangent bundle of the corresponding flag variety. So roughly speaking, Beilinson and Bernstein showed that there is a derived equivalence of the regular block of category O of G. So this is a smaller category than all modules over G, but with some really nice interpretation from quantum mechanics. That's why they studied this category of representations. And the BB localization theorem says that this is equivalent to a D modules, derived category of D modules over G mod B over X. All right, so this is the content of Bernstein-Beilinson localization. I'm sorry, I apologize for the abstractness for this part, but you will get more concrete very soon. But the D modules over X are solving differential equations over this varieties. But roughly speaking, whenever you have a D module, you can take the associated gradient module and that gives you a coherent sheaf until that. So taking associated gradient, that gives you bounded module in the derived category of coherent sheaves until that. Right. So now you have given a coherent sheaf here. This is with actually whenever you have a D module, the coherent sheaf is going to be conical in some sense. So you can take the X algebra in this derived category with the zero section OX. So this is until that. Right. Standard Morse theory says that the objects here in this triangular category lands in a DG modules over DG mod over bounded derived category of DG modules over the DGX until the OX modules. But this guy is nothing but the cohomology ring. So this is cohomology ring of X. So this is Morse theory, and this is using the Hauschel constant Rosenberg theorem. And Chavalet showed that this Borel showed that this guy has a really combinatorial presentation, and this is isomorphic to the Cardan subalgebra of G, quotient Cardan subalgebra of G with respect to Weil group invariance. So this is Borel, who was an Institute of Advanced Studies member, and not very far from New York. So let me say that G contains H, which is Kaplan subgroup, and H is the Lie algebra of capital H. So these are diagonal matrices in here. So you can take the set of polynomial functions on diagonal matrices, quotient symmetric functions on diagonal matrices. And it's really a deep theorem of Wolfgang Zerbel, which showed that this algebra coincides with the center of this category. So this is the center of O0G. Okay, so this uses the work of a lot of famous mathematicians, but in conclusion, that this really abstract category has a very nice combinatorial presentation of its center. The center is the so-called co-invariant algebra. Right? So the theorem of Bennigsen and Bernstein localization has been pushed forward by Roman Berzhkovnikov, who was a student of Bernstein, and his collaborators Arkhipov and Ginsburg. So let me write down this stronger version of the theorem, or strengthened version. So another theorem.
Is this probability Bernstein?
Sorry?
Probability Bernstein?
I don't think so. This is the Bernstein who was Gelfand's student in Russia.
That's him. That's the same Bernstein. Yeah.
That's the same Bernstein?
Yeah.
I didn't know he did probability.
Joseph is the first name.
Yeah, Joseph.
I think so. Bernstein.
Oh, wow.
Yeah, the Russians. Yeah.
It's even more shocking. Yeah, back then, Soviet mathematicians had training in math, physics, and all statistical mechanics and everything, every branch of science. So the theorem has been pushed forward by Arkhipov, Berzhkovnikov, and Ginsburg. Arkhipov right now is in Sweden, and Roman Berzhkovnikov is at MIT, and Ginsburg is at Chicago. And they proved that there is they strengthened Bennigsen-Bernstein localization, that there is a triangulated equivalence between the bounded derived category, so dB of coherent sheaves. But now this is G cross C star equivariant coherent sheaves until with the principal block, the regular block of UQG block. But here, this is the big quantum group we have written about, talked about earlier. Right, there's a quantum Frobenius map on the big quantum group that defines the small quantum group. Right, and
so you're taking Q to the L is
yes, Q to the L is well. Well, there are some constraints on L, but I'll talk about this later. It's not every L set.
And this equivalence is basically independent of L.
Yeah, independent of L. It's only on the regular block. This geometrizes the theorem of, in some sense, Anderson-Janssen circle. Right? This representation category is independent of that. So here G acts where G acts by Hamiltonian actions on the cotangent bundle. Action P star X. Because G acts on X, so on the cotangent bundle it translates into Hamiltonian action, preserving this canonical symplectic form on the cotangent bundle. So sorry, I have to probably switch the marker. And C star rescales fiber of P star X by character by Z going to negative 2G. This is just a fiber-wise rescaling rotation action on the cotangent moment. Okay. So a brief remark of the theorem is that this geometrizes the earlier short exact sequence. This theorem geometrizes quantum Frobenius map because here on this category you can use the quantum Frobenius map to pull back representations of the classical algebra and take tensor products. So in other words, the classical representation of G rep acts on this category. And likewise here on the geometric side, here you have equivariant coherent sheets until that, and equivariant coherent sheets can be acted on by the pullback of representations of G as well. The representations of G acts on here. So the theorem actually tells us the triangulated equivalence intertwines these actions. So this theorem, this functor F intertwines G rep actions on both sides. So it gives you this G action basically is like quantum Frobenius map. All right. So to get information about the small quantum group, you can deduce out of this theorem basically now. So as a corollary, my collaborator and Roman Verskovnikov wrote a theorem. Verskovnikov. Shows that forgetting the G action gives you a triangulated equivalence of small quantum groups. Equivalence. Between finite derived category of coherent sheaves. And now you forget the G action, so it's just C-star equivariant coherent sheaves until that with the principal block, the block of the small quantum group. Supposed to be really small, so you can't even see it. It's a finite dimensional Hopf algebra defined by the kernel quantum Frobenius map. Right. So the content of the proof from the theorem follows from here by a classical Bardach argument. So there's a monad coming from this with the action of rep G. So we forget the G action. There is corresponding theorem for the current, right? So, but as a corollary, so B Verskovnikov and Hofstad is that now you can give a geometric interpretation of the regular block of the center. So the center Z of the regular block UQG is isomorphic to the geometrically the Hausdorff homology, so the Hausdorff homology of n tilde. But now you have to take C-star equivariant Hausdorff homology, and but this guy has a more concrete description, which is the direct sum of ijk hi wedge j of t n tilde k, where I plus j plus k is 0. So this is the coherent cohomology on the right n tilde with its tangent bundle, degree I cohomology, but where the total sum is 0. This is the degree of C-star action. So the C-star acts on the fiber by this character. So every cohomology group acquires a degree that it looks like this. Right?
So the center is the full Hopf
Yeah. No, the center is degree zero.
Okay.
Degree zero. Yeah.
That's what you.
Yeah. Derived center is the
today.
full.
Okay.
Yeah. Right. But well, now this is the theorem of Roman and Hofstad in 2007. I think since then there was no advancement in this direction. Then, well, when I was studying calligraphication of small quantum groups, I wanted to ask Anja Hofstad, who is an expert in representation theory of small quantum groups, so what the center is, because this center is a really special interest to me. They control certain topological quantum field theory and the morphisms of topological quantum field theory. So she told me beyond SO2 this was unknown, and we said, how could it be? This is such a finite dimensional algebra. We should be able to do it. And she told me the theorem she had with Roman, and starting from here we made some progress on how to actually compute this center more explicitly. So from now on, let's focus on the case. So when G is SO3, okay, or SO3 quotient is center, doesn't quite matter. We will look at the corresponding small quantum group for SO3 and what its center is, and I'll tell you the recent progress. Right? I have listed the Harshad homology for G equals SO3. The non-zero ones, degree zero Harshad homology in this table, and I'll report what these entries are in this particular example. Any questions so far? So the classical case of SO2 was known to physicists for much earlier, I think in the 80s, and beyond that, physicists didn't know what SO3 is.
Did you do that algebraically?
Yeah, algebraically. They computed explicitly using the quantum group presentation.
Is it easy to say what the center is?
In this SO2? For SO2, yeah. It's for SO2, the principal block you can just get the Harshad center and the integral in that case. For any finite dimensional Hopf algebra, there is the notion of the integral, and there is this three-dimensional sub-algebra. All right, so, well, first observation, so lemma, it's very easy to observe, is that this vertical column, leftmost column, and bottom row, so leftmost column, of this table, of the Harshad homology table, and bottom row, are both isomorphic to the Colloquium algebra. This is true for more general cases. So. But in this example, I'll just label it what it is. So the Colloquium algebra in this has, in degree 0 has dimension 1, in degree 2 it has dimension 2, degree 1 has dimension 2, degree 2 has dimension 2, and top dimension is dimension 1. It's symmetric with respect to omega. And likewise here it's C2, and C. It's just a simple computation of doesn't use any deep geometry. Just follows from a simple computation. And so it remains to ask what these other three entries are. It seems a pretty simple task. So another lemma we observe is that if G is a simple Lie group, almost simple Lie group up to center, then this entry H0 wedge to Tn tilde of degree -2 is one-dimensional. And why it is one-dimensional? It's actually pretty easy to see. This is because N tilde is a symplectic variety, a holomorphic symplectic manifold. So its tangent bundle, its cotangent bundle is isomorphic to the tangent bundle here because it's symplectic variety. So the cotangent bundle has a canonical symplectic form. Under this isomorphism, the symplectic form gets transformed into a Poisson bivector field. So in calculus, people write so tau is usually written as summation of ddpi wedge ddqi in local coordinates. So this is the x direction, and this is the fiber direction, and fibers have degree -2, as we have seen. So this the local the base direction doesn't have any degrees, so this is of degree -2. Right? So solving this puzzle, we have found that there is a one-dimensional C here spanned by the Poisson bivector field. Right? So what about the other entries? So this now, after observing this, the next theorem is very easy to deduce. We can extend this tau into a full SL2 action on the entire diagram. So there exists an SL2C action on HH0, C star of n tilde, given by tau wedge something. This goes from the tangent bundle T n tilde to degree +2. This is bivector field T n tilde. There is an adjoint operator which is given by contraction with the symplectic forms. Then you find this two globally defined form, and they satisfy this relation that their commutator is actually a scalar depending on the degree. So this gives you an SO2 action. So in particular, let me write this. So this is tau. Wedging with tau, it sent every entry here. And contracting with omega. Has this effect. Okay. Any questions? So, by classical representation of theory of SO2 representation, you know immediately at least this is going to be C tau squared, C tau cubed. All right, and likewise here is this is at least C2, so C2 directs on something. Right. So in this case, the theorem of Lahawka, this is myself. So for SO3, this question mark entry is one-dimensional. So here, let me write this is another copy of C, which is three-dimensional. So because of this SO2 action and its of this fact, Tn tilde and Tn are very, very much like cotangent bundle. We call this the formal Hodge diamond. It's a formal Hodge structure. Like this is a very analogous result as Hodge theory. There's an SO2 action, giving wedging with the symplectic form. Here it's holomorphic and or contracting with the dual.
But SL2 representation is the second diagonal.
The second diagonal. This one?
Yeah.
It's just bunch of three-dimensional representation plus a one-dimensional representation. two copies.
Two three-dimensionals. And
Yeah,
one
two
trivial
adjoint
representation.
representation and one trivial representation. Yeah. All right. So, well, this raises the question. So, what kind of other combinatorial structure have you seen from this table? Well, this leads us to the work of Mark Hyman. Come to the last part, the conjecture. So, around 1994, Mark Hyman from UC Berkeley defined this in his study of Hilbert schemes and points on C2. He's introduced these notions of diagonal co-invariant algebras. Which are just, well, for simplicity, I just define in type A. So this is, you take unvariable polynomial rings, C, x1, xn, y1, yn, and you let the symmetric group act diagonally on the set of two variables. So w xi is xwi. You permute the indices of both of them. And you take their x1, yn symmetric group without degree 0 and without constant terms. So this is the so-called diagonal co-invariant algebra, DCN. Well, when n equals 2, when n equals 3, let's emphasize n equals 3, you can easily figure out the bidegraded dimension. So if you set degree xi equals 1, 0, and degree yi, these are polynomials, so 0, 1, so you can consider the bidegree. So you can easily figure out the bidegree fits into the following table. This is just an easy search online. And this is precisely the dimension table of that guy.
But how do you know it's a algebra isomorphism?
It's not an algebra.
It's not.
It's not. So yeah. So this leads naturally to the following conjecture. So, well, actually, we have a computer program. We wrote a computer program checking this up to SO4 and many entries in SO5, and they all agree. So this seems very valid conjecture. I hope it's myself. So for G equals GLN or SLN C, or GLN C, doesn't matter. So the advantage of using GLN C is that these variables are precisely the Godin part of GL instead of SL. So there is a up to by degree transformation. The center of the regular block of small quantum group, QSLN, is isomorphic to, let's say, degree ij part, is isomorphic to diagonal covariance considered sign representations. So there is a natural symmetric group action on the entire Hausdorff homology groups, because you can use the Steinberg variety and act on use correspondences to act. So both sides are representations of symmetric groups. So, and here you get the sign representation. So the reason why one of the reasons that it prevents this from being an algebra isomorphism is precisely this sign representation here. But this sign representation has to be there from categorification point of view. If you look at the Heck algebra action on the flag variety K0, that is the anti-spherical representation of the Hecke algebra, so it's, which is the regular representation of tensor to be assigned. So that's why this is an analog of that. All right, how much time do I still have?
10 minutes.
Okay. Yeah. So in particular, this conjecture in particular, the dimension of this regular block is quite huge. The dimension of center block of U, Q, S, O, N is n plus 1, n minus 1 dimension. This is the dimension of the diagonal covariance, and it has a lot of combinatorial interpretation. For instance, this is number of unrooted trees between n vertices, and this combinatorial interpretation have some applications in quantum field theory as the Feynman graphs for some quantum fields. So this is probably related to that fact. Furthermore, we also have another conjecture. I think I should start pretty soon. Extending this conjecture to the case of the entire center, so singular. So let me introduce the singular block analog. So in the earlier, when I tried to decompose UQG into a product of indecomposable algebras, let's say A1 plus AK plus AK plus 1 plus AR, something like this. There are many blocks that are similar to the principal block, so these are all called regular blocks. So as algebras they're actually isomorphic by Janssen's translation principle. But the rest of the blocks are called singular ones. And these blocks are classified by the subgroups of the corresponding wall group. So for SO3, the corresponding wall group is S4. S3, permuting diagonal matrices, 3 coordinates. Okay. So here it has 3 subgroups, which correspond, well, the trivial one, which is the 2 trivial ones are the entire group and the trivial subgroup, and the non-trivial one is the Young subgroup S2 contained in it. So associated to these subgroups, you have partial flag varieties. So partial flag varieties. So here, the partial flags fixed by all S3 are just a point. Here is the full flag variety. And in here, in between, this is P2. Right. So more precisely, so to the singular weights, these are the stabilizing subgroups, and then the singular weights are stabilized by this the corresponding parabolic subgroup, which has the Weyl group, whose levy has a Weyl group levy. It's a mouthful, so just give you this correspondence directly. But then the singular blocks, so theorem how to describe itself is that, well, the singular blocks, so the singular blocks, the lambda, so let me label this by lambda, the lambda of UQG are given by the Harshal homology, degree 0 Harshal homology of T star partial flags. Okay. So now you can just count the number of regular blocks, number of singular blocks, and add up their total dimension. So computer experiment tells you that you have the following. So for P2, so for S3, lambda corresponding to S3.
Maybe it's just different.
Yes, right. So this partial flag is just a point. So it's partial homology is one dimensional. When lambda is S2, partial flag is P2, and partial homology has this table, which is three-dimensional. And the lambda is S1, which is trivial group. This is flag 3. Table is over there, so this is Z right. Okay, the table over there, which is 16. So now if you add the number of blocks together with their dimensions, we easily get, so probably for L aunt, L co-prime to 3. The dimension of the entire center, Z UQ SO3, is 4L minus 1, 4L minus 2, divided by 6. So it's a very natural conjecture. Another conjecture of myself is that in general this is a very general Kaplan number dimension of Z UQ SON. So again, here L odd and L and N are co-prime. Then this is N plus 1 L, or N plus 1 L choose that. This is a generalized Kaplan number. Which has very deep combinatorial meaning. So, we have some idea how to prove the first conjecture, but this conjecture is still widely open. I think it's if you can find what's the structure behind the center, you will find the algebra that controls quantum field theory in some sense. So it's very, very important problem. All right, I guess I should stop here.
Questions for Chief? So this L comes from counting the number of blocks. That's
Yeah.
okay.
Yeah, number of blocks is also a very nice, interesting Kaplan combinatorics. It's also given by some Kaplan numbers. Which is
What about the Volhoff-Shilko homology?
okay, we don't know.
It's just universal 3. It's just
Too big to compute. Yeah, we wrote some computer program to compute it, but it's in general it's too hard on laptops.
Other questions for Chief? Okay, let's thank him again. So I think we're going for lunch upstairs. Anybody wants to join? Thanks.